Good morning or good afternoon, applied physics students. Today we're going to be looking at the concept development practice page 25.1 about vibrations and waves. And remember some of the equations that we have in this unit or in this chapter include that our frequency equals 1 over our period, and our period equals the inverse of our frequency. We also have that the speed of our wave is equal to our wavelength times our frequency. So those are some equations that we might use. Remember, this equation means that because wave speed is here, if our wavelength goes up, our wave speed is going to go up and such. So we're going to take a look at some of those kinds of relationships. So vibrations and waves. A sine curve that represents a transverse wave is drawn below. With a ruler, measure the wavelength and the amplitude. So remember, our wavelength is from crest to crest, or from the same spot to the same spot. So I'm going to actually use this, and it's going down, and so it's going to be to here. Okay. And so to measure that, okay, my wavelength is 6.5 centimeters. Now, amplitude, remember, is from this midpoint, this 0 spot, to either the top of a crest or the bottom of a trough, and it really doesn't matter. It should be the same either way. So we'll go over here and measure. And it looks like we're going to say that our amplitude equals we'll just say about 1.4 centimeters. So again, here's our amplitude, right? From here to here, right? That's our amplitude. From here to here, this is our wavelength, lambda, right, which was the 6.5 centimeters. So our wavelength was 6.5 centimeters, and our amplitude was about 1.4 centimeters. Number 2. Okay. A kid on a playground swing makes a complete to and fro swing every 2 seconds. So remember, a complete kind of to and fro, right? That is kind of the frequency. So the frequency of the swing is, because we kind of go and come back, and it takes 2 seconds to do that. Okay. That means that our period is equal to 2 seconds, because it takes us 2 seconds to go forward and back. So the frequency is going to be 1 over our period, which is 2. Okay, so 1/2 hertz. So, okay, our frequency is 1/2 a hertz, and our period is 2 seconds. So period is the amount of time that it takes for us to go through a cycle, okay? And our frequency is the inverse of that, okay? That would be how many would come by in 1 second, okay? And again, we'd only have 1/2 of 1, because this kid would only go either forward or backwards on the swing. All right. Complete the statements. The period of a 440 hertz sound. So 440 hertz, okay? Hertz is a frequency. So if we want a period, we know that our period equals 1 over our frequency. So that would be 1 over 440. So 1/440th of a second. Okay. A marine weather station reports waves along the shore that are 8 seconds apart. So 8 seconds, right? That's a period. The frequency of the waves is therefore this many hertz. So again, frequency equals 1 over period. So 1 over our period, which is 8. So it would be 1/8 of a hertz. So again, one of the things we want to remember is that our period is going to be measured in time, okay, probably seconds. Okay, and our frequency is going to be measured in hertz. So number 4, the annoying sound from a mosquito is produced when it beats its wings at the average rate of 600 wing beats per second, right? So 600 wing beats per second, again, that is going to be, okay, how many cycles there are per second. So this is a frequency. Okay, because a hertz is the same as 1 over second, and this is wing beats per second, so it's 600 per second, so 1 over seconds, which is a hertz. What is the wavelength? Assume the speed of sound is 340 meters per second. So we're going to use this equation from up here, which is speed equals wavelength times frequency. So V equals wavelength times frequency. We want the wavelength, which is this one. So to get wavelength by itself, we're going to divide both sides by frequency. So our equation becomes wavelength equals our speed divided by our frequency. So the speed of sound, they said, was 340 meters per second. The frequency is 600, 1 over seconds. So we're going to do 340 divided by 600. And we'll use 2 decimal places, so we'll call it 0.57, and it's going to be meters because that is the unit of distance that we have here. So again, we reviewed what a wavelength is and how to measure it. We reviewed what the amplitude of a transverse wave is. Okay, and so we have that. Okay, we talked about the relationship between frequency and period, and we calculated a wavelength. Number 5. A pitching machine goes haywire and pitches at 10 rounds per second. The speed of the balls is an incredible 300 meters per second. What is the distance in the air between the flying balls? Right, so this is a frequency. And I know that it's a frequency because it's per second, which is the same as a hertz. The speed is 300, so this is a V. And we want to know the distance, which would be our wavelength pretty much, right? So again, our equation is V equals wavelength times frequency. We want wavelength, so we're going to divide both sides by frequency. So we know that our wavelength is going to be, okay, our speed divided by our frequency. So our speed was 300 meters per second. Our frequency is 10 1/2 which gives us, again, you can use a calculator if you need to, or that's probably math you can do in your head, 30, and the unit is going to be meters. So the distance in the air between the flying balls, which would be the wavelength, right, because those would be like the, counting the crests of the wave, would be 30 meters. What happens to the distance between the balls if the rate of pitching is increased? So this is saying we'd still know we would be using this equation. And so this is asking what happens to the distance between the balls if the rate of pitching, which is our frequency, goes up. Okay? And this is where understanding direct and inverse relationships can be helpful. Because frequency is in the bottom of this fraction, that means that wavelength and frequency are inversely proportional. And when you're inversely proportional, that means if one goes up, the other goes down. So what happens to the distance between balls if the rate of pitching is increased, right? That would mean that my frequency is going up, so my wavelength would go down. It would be decreased. And that should make sense, right? Because if I'm sending a ball more often, the distance between the balls is going to be shorter. Consider a wave generator that produces 10 pulses per second. The speed of the waves is 300 centimeters per second. What is the wavelength? So we're going to use that same equation. Wavelength equals our wave speed over our frequency. Our wave speed is 300 centimeters per second. And our frequency is 10 per second. So again, we're going to end up with 30, but this time our unit, notice, is in centimeters, so it's going to be 30 centimeters this time. What happens to the wavelength if the frequency of the pulses is increased, right? So because frequency and wavelength are inversely proportional, if our frequency goes up, then our wavelength will decrease. Just the same way as it did previously. Number 7. The bird at the right watches the waves. If the portion of a wave between two crests passes the pole each second, what is the speed of the wave? So they've already given me, the length of this wave. And we know that our speed is equal to, we know that speed really should be in units of a distance per time. So what distance does this wave move if he counts 2 crests in 1 second? So 1 crest, here's the first one, and then in 1 second, the second one. So the distance is 1 meter. The time is 1 second. So the speed is 1 meter per second. What is its period? So that's how much time went by. Well, the amount of time that went by was 1 second. If the distance between crests in the above question was 1.5 meters, and 2 crests pass each pole each second, what would be the speed of the waves? So it's still distance over time. Our distance now is 1.5 meters, and it did that in 1 second, which means it's 1.5 meters per second. What would be its period? Again, how much time goes by? It's still 1 second. When an automobile moves toward a listener, the sound of its horn seems relatively, so this is talking about the Doppler effect. And the Doppler effect says that when the waves reach your ears more frequently, you perceive that as a more high-pitched sound. So when the sound of the horn, when the automobile moves towards the listener, the distance between these waves is getting smaller, which means they're hitting my ear more often. And so I'm going to hear that as a high-pitched sound. And when moving away from the listener, the horn seems like here, right, this guy, again, those wavelengths are getting longer. It's taking longer and longer. And so it's going to be low-pitched. The changed pitch of the Doppler effect is due to changes in it's not the speed of the waves. The waves constantly move at the same speed. It's the fact that they're more frequently, okay, the waves more frequently hit or reach the listener's ear. So it's higher pitched when it's coming towards, going towards the listener. So it's due to frequency, okay, the frequency, how often, okay, those waves reach your ears. And because that frequency, how often it's hitting your ears is increasing, you hear it as a high-pitched sound. So, again, we did some calculations, okay, using our equation that relates frequency, wavelength, and wave speed. And we talked a little bit about the Doppler effect. Have a great day. I'll talk to you tomorrow.